Alrighty, so as per usual, these are the things that I'm going to talk about today. There's a lot of examples in this video, which is I thought was enjoyable because it was like doing a lot of little math problems on the chalkboard. But these are the things I'm going to talk about. Time cards are there as well, so if you want to skip to anywhere, they are also in the description below. So you can just click and it'll take you there. It'll be great. Anyway, I'm going to get started. So there are a lot of different ways to assign a size to a set. And generally how I think about these things is that there are like two types of sizes that you can assign. There are absolute sizes, and these are things that aren't necessarily numbers that you assign to a set. And then there are also numeric sizes, which are just assigning a number, or in some cases, a positive infinity to a set to denote how big it is. I've talked about different types of sizing before, and one in particular that I've talked about on this channel is that of cardinality. And cardinality is a little weird because it can fit into both the absolute and numeric sizing buckets. So if you have a finite set, for instance, something that just contains like 1, 2, 3, and 4, you can say that that set has cardinality 4, and that would be a numeric assignment of cardinality. Whereas you can also have absolute assignments of cardinality when sets are infinite. So for instance, the even natural numbers are a set that is countably infinite, and the real numbers are a set that is uncountably infinite. With that as a bit of intuition behind ways that we can describe sets as either absolutely a certain size or numerically a certain size, we can also ask questions about like how different assignments of sizing compare to one another. And what this means mathematically is that you can either have the two sizing methods be logically equivalent, or you can have the first one says more than the second, or you could have it vice versa. Or you could have something where a particular size does not tell you anything about the other size assignment. That is, that they're totally different descriptions of a set. So in this video, we're going to go ahead and approach this question with examples and look at two types of mathematical smallness in particular. So the first one is measure zero sets, which comes up a lot in analysis. And the other thing that we're going to compare it with is sets of first category, which is has more of a topological definition, but it comes up in analysis and topology, and apparently it comes up in descriptive set theory as well. I just haven't seen it in that context. So just to jump right into things, we're going to start off with what is a set of measure zero. And the reason I'm starting with measure zero sets is because generally speaking, at least from my perspective, measure zero sets, at least in terms of Lebesgue measure, and I'll get to what that means here in a second, is a little bit more intuitive, and the definition is a little easier to digest than sets of first category are, or meager sets are. So it turns out that the idea of a measure zero set coincides with this idea of having outer measure zero, which is nice because we're going to have to do a lot less work in order to define what measure zero means. So in order to define that, we need to define what an outer measure is, and we won't have to get into the weeds of talking about measures themselves. So an outer measure is a function mu star from the power set of a set to the positive real numbers with positive infinity, such that 1, the outer measure of the empty set is 0. 2, if A is a subset of B, then the outer measure of A is less than or equal to the outer measure of B. And then 3, if A sub I is a countable collection of sets, then the outer measure of the union of all of those sets in the collection is less than or equal to the sum of the outer measures of all of those individual sets from the collection. Also, again, just to be clear, we're going to be focusing on Lebesgue measure instead of general measures. So Lebesgue measure comes from using a least covering volume. And so to give some intuition, instead of going deep into the gunk of all the symbols and whatnot for time's sake, we can take the example of a singleton set, and we'll say that A is equal to the singleton of 1, and A is a subset of the real numbers, and we'll go ahead and put some open ball of radius d around that set. Now that ball covers our set of just the element 1. We can actually just contract that ball to be an arbitrarily small length. That lends itself to say that the least covering of this singleton set is just something that is arbitrarily small, which means that the outer measure of the set A is equal to 0. So it doesn't seem like we did anything with just a singleton set, but if we go ahead and take what we just determined about a singleton set along with this third property here in the definition of outer measure, which is called countable subadditivity, we actually have a lot more than that. So countable subadditivity with this argument that a singleton has measure 0 actually gives us that any set that is countable is measure 0. And so sets that you probably wouldn't think are measure 0, like the rationals, also have this property by the same argument. The other thing to note about measure in general and outer measure in general is that outer measure and measure are consistent with our ideas about length, area, volume, and hypervolume, depending on what dimension of space you're in. So if you're in an n-dimensional space, then the outer measure of an n-dimensional cube formed by intervals from A to B in each dimension is going to be equal to the length of that interval to the nth power. Again, this doesn't seem like a huge fact or great realization, but it's something that will be important later on in the video. Okay, so now that we have some intuition behind what it means to be measure 0, and we've defined some things in that context, we're going to jump over to defining what a set of first category is, so that we can go ahead and look at some examples that compare the two methods of determining size. Now, a set is of first category if that set is the union of countably many sets, each of which is sigma nowhere dense in the space X. Now, in general, we could be operating in a space with some random sigma algebra, which is what the sigma here is referring to. Instead of defining all that, we can go ahead and disregard the sigma altogether and focus just on what a nowhere dense set is. A set is nowhere dense if its interior of its closure is empty. With what it means to be a nowhere dense set defined in our catalog of definitions that have already come up in this video, we can go ahead and take a look at a non-example of a nowhere dense set and an example of a nowhere dense set and build upon those to get to examples of a set that is not of first category and a set that is of first category. So for our non-example, we're just going to keep it really simple to get used to working with interiors and closures to give you an idea of what that means. So the interior of the closure of the open interval from 0 to 1 is just the interior of the closed interval 0 to 1. And so then the interior is the largest open set. And so then the interior of that set is the largest open set that that closed set contains. And in this case, that is the open interval from 0 to 1. Next, we can go ahead and take a look at the example of a singleton again, but instead of focusing on the real numbers, we're just going to jump up to an arbitrarily high n dimension, because why not? It's math. So the interior of the closure of a singleton is just the interior of the singleton itself. The interior of a singleton is just the empty set. And so now that we have a singleton as an example of a nowhere dense set, we can really just go ahead and overcomplicate this example to make it fit the definition of a set of first category so that we're explicitly giving an example of the definition. So what we're going to go ahead and do is we're going to go ahead and define a countable collection of sets where those x sub i's are equal to A, the single element in our set A. Since our singleton set is also the countable union of these singletons, and since each one of those singletons in the countable collection is a nowhere dense set, we then have that the singleton A is of first category in Rn. So one thing to note here is that the open interval from 0 to 1 doesn't work like this singleton example at all. You can't break it up into countably many nowhere dense sets. And I would go into that a little bit more. It's just I'm not super focused on the large examples. I'm trying to focus on the small ones, and so I'm just going to keep going. So the question to ask is measure zero and being of first category the same thing. So even though the only example I gave of both a measure zero set and a set of first category was a singleton, your intuition should still be that no, they're not the same. And the reason for this is that measure zero is a numeric assignment of size. We're saying that something is zero big, right? And then a set of first category is an absolute assignment of size. We're taking some topological property and saying that that set has that topological thing as a property. But in this comparison, to be a little bit more clear about it, we're going to go ahead and go through some examples to rigorously say that yes, being measure zero and being of first category are different things. The first one to start with, we're going to start with two different examples. And this is going to be the measure zero and being a first category or meager case. So one of the more important examples to give you a better idea of how these things operate is the real line in the plane. So usually I think about this as the x-axis in the plane, but you could do any line through the plane and it would still work. And the reason why this example is important is because it gives us a property of measure and category that is not present in cardinality, the other size that I've talked about in a previous video. And that is that measure and category are context aware, or you could say, and be more technical with it, universe aware. The outer measure of a set is consistent with area in R2. So when we take the measure of a line, that line has zero area, and thus the outer measure of the real numbers, or the x-axis, in R2 is just zero. Similarly, in R2, a set has a non-empty interior if it contains an area. So again, since R, or the x-axis, is just a line in the plane, it doesn't contain any area, and thus the interior of the closure of the real numbers in the plane is just the empty set. So the real numbers in the plane is nowhere dense, and you can proceed accordingly with the same singleton argument that we had before to get to the point where we say that the real numbers is of first category in the plane. So this next example is going to be the Cantor set, which is something that was drilled into me in undergrad. In all of my analysis classes, it came up several times. But anyway, the importance of this set is that it has a lot of really cool stuff going on with it. And it's going to inform our next example, which is the main reason I'm bringing it up. Also, I did a stupid video about the Cantor set too, which is up here if you want to watch that. But anyway, back to the example. So the usual way that the Cantor set is constructed is on the open interval from 0 to 1. At each step, we're going to go ahead and remove the open middle third from each of the remaining intervals. So after the first step, we have 2 intervals. After the second step, we have 4 intervals, and so forth. And we continue doing that until we no longer have intervals. The Cantor set is then defined as the intersection of all of these steps in the construction process. Keeping in mind that our notion of outer measure and measure are consistent with length, we can go ahead and say that the outer measure of each step is less than or equal to 2 to the n times 1/3 to the n, which is just equal to 2/3 to the n. And since that is a value between 0 and 1 to the nth power, after we iterate infinitely many times to get down to the Cantor set, that length is going to be 0. The other thing to note here is that by construction, Cantor sets contain no intervals. So there is no interior of the Cantor set in terms of the universe being a real line. So we can also say that the Cantor set is of first category in the real numbers. And so the reason why the Cantor set is going to inform our next example, which is going to be something that is not measure 0, but also meager or of first category, is that the example of something that is not measure 0 and meager is that of a fat Cantor set. So the particular fat Cantor set that I'm going to construct is the Smith-Volterra-Cantor set, but you can do very similar constructions for certain values to get another non-zero measure set. So what we're going to do is that instead of removing the open middle third, we're going to go ahead and remove the open middle fourth from each of the remaining intervals at each step. So after step 1, you get 0 to 3/8 and 5/8 to 1. After the second step, you get 0 to 5/32, 7/32 to 3/8, 5/8 to 25/32, 27/32 to 1. And then the construction continues from there. For every n, we can use our same intuition that outer measure is consistent with length. And so the outer measure of each of these steps in the fat Cantor set construction is going to be less than or equal to 1 minus 2 to the n times 1 over 4 to the nth power. So each step in the construction, this will render out to 1 minus 1/2. So the measure, or the outer measure rather, of the fat Cantor set must be less than or equal to 1/2. Similarly to the regular Cantor set, the Smith-Volterra-Cantor set does not contain any intervals. And we get that the fat Cantor set is a first category as well. The non-examples for both of these is pretty easy. We can just look at the real numbers in the real numbers. The real numbers is dense in itself, which is, it's a weird statement. Again, I'm not going to focus too much on it, but that's a thing. And then the outer measure of the real numbers is just positive infinity. So it definitely doesn't have measure 0. And then the last example that we're going to go ahead and talk about is going to require more board space. So this is going to be an example of something that is not meager, but is also measure 0. So to start off, we're going to set some definitions for what our indices mean before they show up. Because if I just throw 2 indexes at you, it's going to be very confusing. And the first time I saw this, I was very confused because nowhere did they note what the 2 indices were for. So n will index sets. It's just going to be a counter on sets. That's all it's going to do. And I will be an index on the rational numbers. We can do this with a countable index because the rationals are countable. We're going to go ahead and first define a sub n, which is going to be equal to the union of u sub ni, where u sub ni is equal to the ball of radius 2 to the negative I power over n about the rational q sub I. So if we go ahead and take an example of how we can go ahead and index the rationals with natural numbers, we can go ahead and work our way through a fraction table where wherever we've hit an entry that we've already visited before, we'll just block it out. And we're going to start our ordering with 0 is equal to q0. The other thing to note is that the path through this fraction table is going to include half of our nodes. At each stop, the next thing in the list is going to be the negative of that number. So 0 is the 0th rational, then 1 will be the first rational because that is where we stopped first in the path, and then negative 1 will be the next rational before we move on to the next box, which is 2, which will be the third rational, and then negative 2 will be the fourth, and then 1/2 will be the fifth, and then negative 1/2 will be the sixth. So to give some intuition about what this set looks like, I'm going to go ahead and draw out what the first 5 UNIs are in the n equals 1 case, and then again in the n equals 2 case. And so this is a really bonkers construction. It looks like everything's just going to go to just the rational numbers, and that's all you're going to get. But that's not what happens. And in fact, at any step in this construction, you're going to have an interval somewhere where 2 rationals have had overlapping intervals. We can see this in the n equals 1 case with 0 and 1. But as we get smaller and smaller, you have to go further and further out the list of rationals to find 2 rationals that have intervals that intersect with each other. So with that out of the way, we can go ahead and go through some outer measure calculations. So I made a stupid mistake and I wrote everything in terms of radiuses instead of diameters. So there is a 2 missing in my calculation, but it's fine because the limit is going to come out the same way. It turns out that this evaluates to 4 over n, and then you take the limit as n approaches infinity, and you get 0. And so the outer measure of this thing is 0. So at this point in the video, you probably expect me to go to the board and continue to talk about why this set is not meager or is not a first category in the real numbers. And I did do that on the board, but then when I was filming the voiceover parts where I also explained stuff to the camera about what I was writing on the board and what I'm talking about, we had this moment. And this was the moment that I realized that what I had written on the board about why this thing was not meager was totally wrong. So in order to remedy that, I've gone ahead and added a section to the description below that gives a little bit of intuition behind why this ugly construction of a set is not meager, and also some other examples of measure zero sets that are also not meager that might be a little bit more intuitive. Anyway, with that being said, we're gonna go ahead and cut to me being awkward about the outro as I usually am. So yeah, that is all I had for you today. I'm not really sure if I'm gonna be putting out videos over the next 2 weeks. If I do, it will be a surprise to me because I will be moving. And it's gonna be terrible because it's gonna be, you know, like across the country. And it's happening in a week. And I haven't packed anything. Oh, that's a lot of, oh, okay. If you enjoyed this video, you can give it a thumbs up and subscribe for more mathematics stuff. As always, I am Nathan, this is Chuck, and I will see you after I've moved, I think, maybe, unclear. Bye.